Chapter 4. Classical Measurement. For point 1, capturing small measurements in time-integrable systems. Measurement with the highest sensitivity occurs where the measurement event is repeated, often in arrangements where a key value is summed over time. Thus, it is natural to look to time-integrable systems as a key component of a sensitive detector. An oscillator is an example of such a system, for which a brief recap is provided next. After that, we do one last generalization, the addition of noise fluctuations, fundamentally present due to thermal noise sources, to get a description of actual experimental limits. Initially, to build from the CM results shown in Chapter 3, we will develop the damp-driven oscillator with noise and see what minimal detectable force acting on the oscillator mass is possible. This describes a contact method for force detection. Direct contact methods for actual detection are more typically based on strain gauges or piezoelectric elements that can directly couple into electrical, resonance, circuits, note conversion of signal to electronic form, which will be the norm. Indirect contact methods based on capacitance meters do best in this category, where the measurement of a displacement directly alters the capacitance, via plate separation directly related to displacement. The resting capacitance is chosen in a circuit operating at resonance, or on the steep part of the resonance curve, such that circuit frequency shifts are most notable by a secondary circuit, indirect contact, measurement device. Examples of the capacitance meters get into circuit descriptions that, although straightforward, are outside the scope of this description, so won't be discussed further.
Optical non-contact methods offer the greatest sensitivity, and those will be briefly discussed following more explicit results for the contact methods, since the presentation of an oscillator direct contact detector demonstrates many of the key concepts and limiting factors. Note that the most extreme non-contact detection is quantum non-demolition, but that will not be discussed. Notes from the LIGO project, and were obtained from Professor Drever's course PH 118 CA 1988, in Appendix B. The 1988 The LIGO contact list shows less than 30 on the project, including myself, a graduate student at the time. There are now over 3,000 contributors on this project worldwide. 4.1.1 Recap of Damp-Driven Oscillator. For the damp-driven oscillator we have the ODE. See equation 4-1. With solution. See equation 4-2. Where.
See equation 4-3. Once steady-state motion is achieved, x of t approximately equals b the cosine of gamma t plus delta. Energy absorbed from the external force matches that dissipated in friction. We have the rate of dissipation due to friction previously as minus 2 script f, where script f script equals 1/2 alpha x squared equals lambda mb squared gamma squared the sine squared of gamma t plus delta. With time average, 2 script f bar equals lambda mb squared gamma squared. Thus, the energy absorbed per unit time is lambda mb squared gamma squared. Now, if we want the integral of the energy absorbed at all driving frequencies, the absorption will be dominated by the frequencies near resonance, for which the integral approximates as pi f squared of /4m. For point 1.2 damped-driven oscillator with noise fluctuations. Let's now consider the damped-driven oscillator with noise fluctuations and determine the minimum detectable force that the system can provide. This is the scenario with realistic noise fluctuations that provides an accurate limit to the sensitivity of measurement. Let's start with the new ODE with added noise fluctuations term f sub f of L.
See equation 4-4. Where the steady-state result from before, without fluctuation noise forces, was x of t approximately equals b the cosine of gamma t plus delta. Is there still a steady state but with a slightly more general form? First, consider that the amplitude relation time is given by tau sub m equals 1 divided by lambda, and we are assuming that the intention is to do precise measurements, so we seek a minimal damping, thus a maximal relaxation time tau sub m, thus effectively steady state compared to the time of measurement, and the time of the f of t effect meant to be detected. We thus will have the steady state form indicated with possible time dependence in the constants at a guess. Trying the guess and validating it then proves this to be correct, and switching now to the notation of Brzezinski, we will summarize the derivation of Brzezinski shown in the appendix of titled Statistical Criteria for the Determination of the Excitation of an Oscillator by an External Force.
See equation 4-5. Our assertion of a detection event will be a probabilistic one, especially given the addition of a stochastic process, noise fluctuations. We wish to consider the probability that a force event f of t occurring in time tau that falls within the time frame of the measurement. The detectability of such an event requires discerning it from false signals from the fluctuation noise f sub f of L. In turn, the nature of the detectability must be examined for both. In both cases, what we are looking for is a change in the amplitude of oscillation according to the difference A of tau minus A of 0, and in the case of the fluctuation noise this limit must be qualified to be valid with probability 1 minus alpha. This approach is motivated by the expression for the probability density of an arbitrary distribution of amplitudes of oscillation after event time tau.
See equation 4-6. Where? See the next equation. The statistical error of the first kind formalism, with 1 minus alpha, now takes the form. See equation 4-7.
Following Brzezinski's analysis, we will now consider solving the integral for two cases. A of 0 equals 0 and A of 0 equals sigma. We will find that the evaluation of minimal detectable force is roughly the same regardless of initial value of the amplitude, while the energy exchange with the oscillator is significantly affected by initial amplitude. Also, following Brzezinski, we shall assume our noise source is purely a thermal noise source. This is the best-case scenario as thermal noise sources are fundamental in physical systems in a variety of ways. See for derivation of these noise sources in circuits. For example, if we assume just thermal noise, we then have, according to the thermalization temperature T, the following. See equation 4-8. Solving the integral and substituting, we then get. See equation 4-9.
Thus, if we start a detection event with A of 0 approximately equals 0, and we see the amplitude grow in time tau such that A of tau is greater than open bracket A of tau close bracket sub 1 minus alpha, then we have with probability, or reliability, 1 minus alpha, that an event has occurred. As noted by Brzezinski, what we have is only a threshold condition thus far describing what to do if the threshold is met. If the threshold is met, then we are saying no detection event, e.g., that f of t equals 0, but this may only be due to an unfortunate cancellation of event force and fluctuation forces. To assess the error that can be introduced from this, Brzezinski introduces a measurement of a statistical error of the second kind corresponding to the probability of having f of t is not equal to 0 while still having the below threshold event A of tau is less than open bracket A of tau close bracket sub 1 minus alpha. Specifically, consider the force f of t when there is no fluctuation force present, and such that the change in the amplitude in time tau is to a value normal gamma that is greater than the threshold, such that we have.
See equation 4-10. With gamma is greater than or equal to 1. This lays the foundation for evaluating the error of the second kind. Further details are in. The conclusion is that a simple constant factor, (1), is all that would modify the threshold condition for detection event. Let's now relate the minimal detectable change in amplitude to the energy imparted or extracted from the oscillator using the form with gamma above. See equation 4-11. Returning to the simple case of f of t equals f sub 0 of sine omega tau in time interval from 0 to tau, and 0 force outside that time interval, then we have the linear growth in amplitude according to.
See equation 4-12. And requiring that normal gamma is greater than open bracket A of tau minus A of 0 close bracket sub 1 minus alpha then gives the minimum detectable f sub 0. See equation 4-13. Where ρ is a dimensionless reliability factor that ranges between 2.45 and 4.29 for typical reliability values alpha, see table A1 in. A similar analysis for the case where A of 0 approximately equals sigma at the start of the detection event reduces to the same formula with reliability factors ranging between 1.96 and 3.88. Thus, the minimal detectable force is roughly the same regardless of initial value of the amplitude and has the form.
See equation 4-14. 4.1.3 Optical non-contact methods. There are two types of optical measurement that we will focus on here. 1. Knife edge, and 2. Self-interference. The knife edge methods involve an optical lever in some capacity. If we shine a laser beam on a mirror and measure its fluctuations on a screen distance d away, then the projected signal is twice as great if we simply double the projection distance to 2D. More common, and a blend of type I and II, is to use a diffraction grating, where the gain effect is multiplied according to the separation in the movable diffraction grating that is part of a beam transmission measurement, involving a second, fixed, diffraction grating. The most sensitive of the optical self-interference type of detection events, however, typically involves a Michelson-Morley interferometer. The basic idea is that the beam is split and allowed to interfere with itself such that perfect cancellation is tuned at the transmitted part of the beam splitter. When a displacement in the mirror or mirror cavity distance occurs, we then see a slip from the cancelled state and see a flash of light according to the extent of non-cancellation, which is related to the strength of the signal. As with many of the detection methods, an evaluation of sensitivity often looks promising, but actually, obtaining the physical device parameters needed are often unobtainable. With the interferometric approaches, however, what is needed is often within reach, using very powerful lasers, highly reflective mirrors, exquisitely stabilized mirrors, and beam splitter mirror for starters. Turns out this can be done, but it's a matter of scale.
Work I participated on involving the prototype LIGO detector in the 1980s was an instance where the interferometric methods were demonstrated to work extremely well. But the prototype interferometer arms were 20 m long, not 2 kilometers, as they would eventually need to be. So the scale of vacuum was very different. The laser interferometer cavities are maintained at high vacuum to eliminate noise, and more importantly, avoid a destructive process on the very expensive, highly reflective mirrors. An EM effect to be discussed results in uncharged dust, taking an effective charge and in the non-uniform electric field of the cavity. The result is the dust is driven into the mirrors, causing their steady degradation. This, and other scaling issues, required another 30 years of development until the LIGO project finally came online with the first gravitational wave observatory, Nobel Prize for Kip Thorne, et al. In the 1980s, when I participated for a few years, before shifting into more theoretical issues, to be described in, the LIGO group was quite small, about 30, see the old directory in Fig. B.1. The scaling by 100x in the device size was partly met by a 100x rescaling in the group effort by the year 2020.
A proper description of the LIGO detection methodology would take us to far afield into laser noise properties and optical cavity properties, but a high-level description is still given. First, the L-shaped interferometer is doubly important for the type of detection event sought, which for LIGO was a gravitational wave. Such a wave would be measurable only via its quadrupole effect, with orthogonal detector arms, see Book 3 for details, whereby one arm of the interferometer is lengthened while the other is shortened, providing a change in the interference signal. This for the quadrupole wave hitting the detector perfectly transversely and aligned on the detector arms. Second, the laser noise, multimodality, directly relates to shifts in the main mode that is being locked on, which is a noise problem, thus requires something to clean the laser noise. At the time I was working at LIGO, the resonant cavity that was employed for this task was named by Ron Drever as the dewiggler. Thus, there is a laser cavity, high-powered, that feeds into a mode cleaner, the dewiggler, that then feeds into the L-shaped interferometer. And, third, there is the matter of stabilizing the arm lengths against positional fluctuations in the frequency band of interest for detection. In essence, the end mirrors and beam splitter mirror must all be servoed to fixed position relative to each other. The whole system floats with respect to the surrounding vacuum chamber, while relatively locked. In the end, specialized signal processing is needed for detection of a known signal profile or group of profiles. In essence, a specialized filter based on matching to the signal sought is employed for optimal detection capability.